Hi friends, today let's read this paper called Linformer. Linformer is a linear optimization trying to solve the quadratic time and space complexity in transformer attention. Let's start by a recap with original attention in the transformer architecture. Attention is a way to process sequential data. It models from the database paradigm with key, value, and query. Given a sequential input, self-attention projects the input sequence into query, key, and value. It measures the query and key similarities by first doing a matrix multiplication, and then doing scaling, and then softmax. After softmax, it got the attention matrix. It calculates final attention head by doing a matrix multiplication between the attention matrix and the value matrix. So there it gets the final attention head. So let's now start doing a quick complexity analysis. So say you have your input sequence length as n. You project it into three different matrices, which is query, key, and value, and they each have size by d. And then you have the query and key matrix multiplication. So this one, the time complexity is O(n squared d), and the space complexity is O(n squared). Scaling is a linear operation, and after that you have softmax. For the softmax, the time complexity is actually O(n squared because you cannot have to do this softmax for every element in the matrix. So similarly, the space is also O(n squared. And here you do another matrix multiplication between value matrix and attention matrix. So the time complexity is O(n squared d), and space complexity is O(n squared). So in summary, we can see here is that the overall time complexity is O(n squared d), and the space complexity is O(n squared). As you can see, both time and space are of quadratic complexity. When we have long sequences, hundreds or thousands of sequence lengths, the vanilla attention becomes hard to scale. And this is what Linformer comes to fix. Now let's dive into the paper. So Linformer is actually from Meta. You can search their code base. I think they have an implementation in PyTorch. So let's start with theorem 1. So Linformer starts by claiming that self-attention is low rank. Low rank means that attention matrix can be represented by a smaller matrix with less number of rows and columns. To understand this theorem, let's first take a look at the mass of attention. So the paper status here. As you can see, these WQ, WK, WV, they are projection matrices. Time complexity for P is O(n squared d). So as a recap, actually understanding this P is pretty important. What P is doing is that it does projection, like for key and V input, and then it does scaling, and then lastly it does the softmax. So this is a part where Linformer is trying to optimize. What theorem 1 is saying is that the matrix P we just discussed is low rank. Matrix P is of shape n by n, and theorem 1 is saying that P's information can be represented by a matrix with less number of rows and columns, which makes the computation less expensive. So it expresses this claim in this way. For any QQV, you can have a matrix P tilde that can basically replace P. The error of this replacement is very minimal. The rank of P tilde can be very small. But how does the paper prove this theorem? It actually proves it in two ways. One is mathematically. It uses single value decomposition to prove it. And the other, it also draws an empirical diagram to illustrate the point. Let's start with more serious proof in math. We just talked about there exists a low rank P tilde that is able to replace P. But what exactly is P tilde? The proof answers this question. It starts by rewriting P into two components. One is exponential of A, the other is diagonal matrix. The only place that often mentions about diagonal matrix is singular value decomposition. So take a look, P tilde here. P tilde equals to exponential A, diagonal matrix A, and then RTR. So this is a square matrix, this is a square matrix, and this is a diagonal matrix. What is this? This is single vector decomposition. P tilde, it can be written in a way that is the single vector decomposition of P. When you are making a low rank version of P, which is P tilde, you are actually just extracting partial information from the diagonal matrix and from the corresponding square matrix. What this paper is claiming is that when you have k equals to this value, P tilde can approximately replace P. Let's recap about this math proof. First, it rewrites the P matrix into a square matrix times a diagonal matrix. And then it constructs the P tilde matrix by rewriting it in the format of singular value decomposition of P. And lastly, it used GL lemma to prove that when the rank of P tilde is of certain values, you can use P tilde to approximate P with very low error. The paper also gives an empirical data to demonstrate that the low rank P tilde has most of the information from P. As you can see from these three diagrams, they are the self-attention matrix P of a pre-trained transformer model. This model has multiple layers of attention. The sequence length is 512. That is why, as you can see in the x-axis, the largest eigenvalue index is 512. And as the eigenvalue index increases, the P tilde is closer to P. Most of the values in P can be captured for the first few eigenvalues in this diagram. When the eigenvalue index is 128, we can capture greater than 90% of the values in P. So far, we have known that self-attention is low rank, and the paper provides both mathematical proof and also their empirical diagram. But still, there's a major drawback. This approach requires singular value decomposition for each self-attention matrix, which is not very practical since SVD adds more layers of complexity and doesn't practically solve the issue of quadratic complexity. So that's why this paper introduced theorem 2. The impractical side of using theorem 1 is that you have to run SVD for each context mapping matrix P. So every time the query changes, you have to run SVD again with random projection. The twist here is that theorem 1 bundles query and key together and it doesn't fundamentally solve the quadratic problem. In theorem 2, it solved this by separately projecting keys into lower rank as well as the value matrix. They've introduced two random projection matrices, E and F. So they project sequence lengths from N to K. Matrix E projects key into a lower dimension from N to K. Matrix F does the same thing for value matrix. The paper provides some visualization of how it works. This is projection E, this is projection F. Like after projection, key and value will become lower dimension in their sequence length dimension. And this paper proves that using E and F projection for key and value to get us low rank keys and values can approximate the original keys and values and is error bounded. And when training the model in practice, matrix E and F can be learned via gradient descent. So to summarize, theorem 1 and theorem 2, theorem 1 claims and proves that self-attention matrix P is low rank, and theorem 2 proposes a practical way to get the low rank matrix. As every other machine learning paper, this paper also provides some training techniques. I think in which one of the most important thing to notice is what they mentioned about parameter sharing between projections. So they are saying that for projection K and V, the matrix K and V we just talked about, you can reuse it at different level. Like for example, the first one is saying that you can reuse E and F, use the same E and F across all your heads in your multi-head attention. The second kind of sharing you can use the same compression matrix E and F to compress both key and value. And lastly, there's another layer-wise sharing is saying that reuse the projection matrix E for all layers. I think this technique is quite important when you have a lot of heads in your multi-head attention. Sharing these compression matrix will help reduce memory. Their experiment results is also saying that when you maximize your reuse of compression matrix, that is to say, you use layer-wise sharing, it has similar results with other kinds of sharing. So lastly, let's talk about experiment results. Here is their model efficiency results. Left-hand side is time saved, right-hand side is memory saved. I think one thing to keep notice here is that you see like it does great job in memory saving. But essentially you have O(n) squared before, now you have O(n)k. And similar for time saving is O(n) squared d to O(n)kd. So let's also take a look at the model performance results. The first one is saying that increasing k doesn't improve performance or decrease performance. It's the same story here and same story here. So what is this telling is that the paper wants to argue that k can be constant and independent of k. And that's what this diagram is trying to tell us. The reason why it's called Linformer is because it converts O(n) squared to O(n)k. And this type diagram is telling you that k can be constant and independent of n. Let's conclude right now. Linformer, compared to the regular self-attention, it projects keys and values into a lower dimension at the dimension of the sequence length. So instead of n by d, key and value will have k by d. This reduces the cumbersome matrix multiplication in self-attention from O(n) squared to O(n)k. And the paper also argues that k can be constant and independent of n, which make their attention linear and thus save time and space complexity. So that's it. I hope this is helpful. Thank you for watching.